Let's take a look at the difference between series resistors and parallel resistors. If the resistors are in series, what do we know has to be true about them? What has to be the same? What has to be different about those resistors if they're in series? They've got to have the same current, right? Because there's only one path. So all these resistors have the same current. And I usually describe this as the full current, because it's not like the current coming in gets split up amongst them. They all get the same current. If you've got, let's say, 10 amps of current coming in, they all get that 10 amps of current. It's not like it gets split into thirds. And yeah, they have different voltage drops, because voltage drop is associated with a difference from location to location. Current is just a property of this path. This path has a certain amount of current. But voltage drop, from here to here, you've got a delta voltage. From here to here, you've got a delta voltage. And from here to here, you've got a delta voltage. And what can we say about those three individual voltage drops compared to the voltage drop from beginning to end? If we've got a high voltage at the beginning and a low voltage at the end. What should we assume about each of those voltage drops individually as compared to the voltage drop from beginning to end? Yeah, they're going to sum up to, I wouldn't say sum up to the voltage at the beginning, but sum up to the total difference in voltage. So this delta voltage plus this delta voltage plus this delta voltage adds up to the total delta voltage from here to here, which might be just the voltage provided by the battery, or maybe there's a more complicated circuit involved. So the resistors have to split up the available voltage. Are there any circumstances where they would split it up evenly? Like, let's say there's 12 volts available. Are there any circumstances where that would split up into 4 volts, 4 volts, 4 volts? When would you expect them to split up the voltage evenly? Yeah, if they're all the same resistance. If these are all the same resistance as each other, there's no reason why one of them would get any more or less than the other. So the voltage would split up evenly, in this case into even thirds. If they're different resistances though, how would you decide, or how would you expect which one would get more voltage? What's our usual formula for delta V for a resistor? Remember, they've all got the same current. And yeah, it's going to have to do with resistance, because what's our usual formula for delta V for a resistor? Yeah, negative IR. Let's ignore the negative for now, because we just want to look at how much the voltage drop is. We know it's going to be a negative because it's losing voltage. We're assuming they all have the same current if they're in series. Same current suggests that more resistance leads to if R is very large, then what does that tell you? Yeah, a greater voltage drop. So if they're in series, they have to have the same current. They split up the available voltage, and whichever one has more resistance gets a larger voltage drop. And have you seen the idea of power yet? The idea of how much energy per second. Do you have any formulas for power yet? And what formula could we use here? In general, we define power as energy per second, change in energy over change in time. How much energy is being transferred divided by how much time it takes. But have you seen how you can manipulate those into expressions involving current, voltage, and resistance? We were defining current earlier as charge over time. Yeah, if we just multiply current times voltage, because current is defined as charge over time, and voltage is defined as energy density, energy over charge. If you multiply those ratios together, what's going to happen? Yeah, you just get energy over time, which is the definition of power. So power is defined as energy over time, but for an electrical circuit element, that also happens to equal current times change in voltage. So this is a very useful way of calculating power draw or power dissipation, how much power a circuit element provides or how much power a circuit element uses up. For instance, if you have a battery and you know the voltage of the battery and the current passing through the battery, you can just multiply those to find the power produced by the battery, how much energy per second the battery is providing. Or for a light bulb, you multiply the voltage drop for the light bulb times the current flowing through the light bulb, and that tells you the power leaving the light bulb, the amount of light and heat per second emanating out of the light bulb. So for instance, for a light bulb, you can calculate power to get an idea of how bright the light bulb is. In this case, more voltage or greater resistance means more voltage, but they all have the same current. So whichever one has more resistance is going to be brighter if they're light bulbs, or louder if it's a buzzer or something like that. But more resistance, if they're in series, more resistance means more voltage and therefore greater power. Any questions on that so far? And also, since they all have the same current, if you have those voltages being added up, I mean, the whole idea of these delta voltages is that these individual delta voltages add up to the total delta voltage. Delta V total equals delta V1 plus delta V2 plus delta V3. But each one of those individually can be written as negative IR. Same current because they're in series, so we don't really need to even label these as I1, I2, and I3. It's just the current. And since it's the same current, what can we do with that in every term? Yeah. Well, we can't really just add them together to get 3i, because it's not just negative I plus negative I plus negative I. It's negative I times a coefficient plus negative I times a coefficient. Yeah, we can factor that out. Factor out negative I, and what are we left with? Yeah, we just have the sum of those resistances, R1 plus R2 plus R3. So we now have delta V total equals negative I times a resistance. And this resistance here, if we just add together all the resistances, this acts like just negative I times R. Specifically, we call this R total or R equivalent. So what this tells us is if the resistors are in series and all have to have the same current, then they can be treated as acting like just one big resistor whose resistance is the sum of all those individual resistors, all those individual resistances. So we can total that up by just adding the resistances. And of course, it doesn't have to be exactly 3 resistors. This still works if it's 2 resistors or 5 resistors or 17 resistors, as long as they're all in series with each other, as long as they have to have the same current, then you can just add their resistances to get the total resistance. Any questions on series so far? Then let's take a look at the same ideas in parallel. If they're in parallel, what has to be the same about all the resistors? Power, it's more what makes a bulb shine brighter. Power is how much energy is is being transferred per second. So for a light bulb, for instance, power is how much energy is leaving the light bulb per second as light and heat. For a battery, power is how much energy the battery is providing per second, because the battery is providing energy to the circuit as time passes. But in general, power is rate of energy transfer, how quickly energy is being transferred from one place to another or from one form to another. And so it's defined as change in energy over change in time. It also equals current times voltage drop. So if you know the voltage drop for some circuit element, like a light bulb or whatever, and you know the current flowing through it, then you can just multiply those to find the power. So this is true for resistors and for batteries. Resistors are using up power. Batteries are providing power. For resistors, though, there's also a couple other formulas that are often useful. Because for a resistor, we can replace delta V with IR. And I'm going to ignore the negative because we don't really care about sign here. We're just looking for how much power. If you replace delta V with IR, what does this turn into? Yeah, the I times R could be abbreviated as I squared R. So this is another perfectly valid formula for power if you're talking about a resistor. This one only works for resistors, of course. This one, I times delta V, that works for resistors and for batteries. But if you're specifically talking about a resistor, you can just take the current flowing through the resistor squared times the resistance. And this is often useful as a way of finding power because you don't need to know the voltage drop. You just need to know the resistance, which is constant, and how much current is flowing through it right now. Or another alternative, instead of replacing delta V with IR, you could rewrite current as, solve this for current, you get delta V over R. Again, ignoring the negative sign for the moment. Replace current with delta V over R, the delta V's combine, so we get delta V squared over R. Or sometimes that's just written as V squared over R. The greater the resistance, yeah, in this case, the greater resistance means greater voltage drop and therefore greater power. And in that case, this formula would probably be most useful because we know the bulbs all have the same current. Actually, either one of these, I guess, would be useful. They all have the same current, so more resistance directly means more power. Or you could go back to the idea that you know the one with greater resistance gets more voltage. More voltage means more power. Well, this one, I guess, wouldn't really be useful, though, because the voltage is different and the resistance is different. This one, I think, would be a more effective formula to use because you know they all have the same current if they're in series. Same current means more resistance directly leads to more power. And therefore, if these are, let's say, 3 light bulbs with different resistances in series, the one with more resistance is going to be brighter. Any other questions on that so far? All right, let's try the same approach in parallel. In parallel, what are we assuming is the same about all the resistors? They all have to get the same what? Yeah, they all get the same full voltage drop. If we've got high voltage on one side, low voltage on the other side, resistor 1 is a path from high voltage to low voltage. Resistor 2 is a path from high voltage to low voltage. Resistor 3 is a path from high voltage to low voltage. Each one of these resistors is a path from the same starting high voltage to the same ending low voltage. So they all get the same full voltage drop. And that might be the full voltage of the battery, or maybe it's connected to more complicated arrangements of stuff, so it's not getting the full voltage of the battery. But the important thing is all three of these are getting the same full voltage from here to here, because they're all paths from the same starting point to the same ending point. But what happens to the current? When current flows into a junction like this, what's going to happen to it? Yeah, the current is going to split. You get some current flowing in, and it's going to split three ways. And then those currents, of course, join back together into the final current, which is the same as the current coming in. So current coming in splits into three different subcurrents, which then join back together. And we could even use the junction rule for that. We could say I1 plus I2 plus I3 equals, let's say I sub 0 is the current coming in. And under what circumstances would you assume the current splits up evenly? Like 1/3, 1/3, 1/3. When would you expect that to happen? Yeah, if they've got the exact same resistance, there's no reason for a current to prefer going one way or the other. So it was split up evenly. Or if they're different resistances, how would you decide which one gets more current? Which one of these, if these are different resistances, which one would you expect? Yeah, the one with less resistance gets the more current, gets most current. With least resistance getting the most current. And of course, that doesn't mean the other ones don't get any current. The current does split up. The one with the path with the least resistance gets the most of the current. The path with more resistance still gets some current, just not as much. And they should be proportional. Like for instance, if this resistor is 10 times as much resistance as this one, that means this resistor should get 1/10 as much current as this one. The resistance and current are inversely proportional to each other because they have to have the same voltage. Same voltage, twice as much resistance means half as much current. Any questions on that so far? And putting that all together, I think it actually makes more sense to use the junction rule here to go back to I1 plus I2 plus I3 equals I0. But going back to Ohm's law, delta V equals IR, if you isolate I here, what do you get? I equals what? Yeah, delta V over R. And again, I'm going to ignore the negative for the moment. Or alternatively, you could assume that there's a negative in every term, so we just multiply both sides by -1. And so these become delta V over R1, the same delta V over R2, and the same delta V over R3. And we know it's the same delta V because that's really what parallel means. Parallel means that they're all getting the same voltage drop. And since it's the same voltage drop, we can factor out delta V from everything. If we factor out delta V though, we're not left with R1 plus R2 plus R3, we're left with 1 over R1 plus 1 over R2 plus 1 over R3. So this is how we would add resistors together if they're in parallel. Because they have the same voltage, the junction rule turns into something over R1 plus the same thing over R2 plus the same thing over R3 when you substitute in Ohm's law. So that means instead of just adding the resistors R1 plus R2 plus R3, we're going to add their inverses. They're adding reciprocally. 1 over R1 plus 1 over R2 plus 1 over R3. And instead of just adding up to R equivalent, that adds up to 1 over R equivalent. So this is how you can combine resistors if they're in parallel. Instead of just adding the resistances, you add the inverses of the resistances, and that doesn't give you the result, that gives you the inverse of the result. So you still have to invert it again at the end. Same change in voltage. Yeah, they all come back together at the low voltage point. The idea is you've got some path that splits into several subpaths, and then those paths join back together. If they don't join back together at some point, they're not really in parallel. And they don't all have to join at the same point to begin with. Like this one, it looks kind of like this path splits into 2, and then this second path splits into 2 again. But overall, you've got 3 paths that join back together. And all these paths start at the high voltage point, and they all end at the same low voltage point. Any other questions on that so far? And let me get a quick picture of this because I'm sure I'm going to be referring back to it later. All right, any other questions on these core concepts before we try out an example? All right, then let me draw up a circuit and we will try analyzing it. Okay, I think that should work. So here's an example of a circuit. We've got a battery, which is a voltage of 36 volts. And we've got these 4 resistors, R1, which is 2 ohms, R2, which is 3 ohms, R3, which is 6 ohms, and R4, which is 5 ohms. And we want to figure out the currents in this region, in this entire circuit. And also, ideally, we should know the voltages for everything, the delta voltages for everything anyway. So that's usually what we mean when we say we want to analyze a circuit. We want to figure out how much current is flowing through each branch and how much voltage is there at each junction, each location. And so the first thing I would do is just start labeling currents. We don't know what any of the currents are at this point, but we can at least start labeling them with variables. How many different currents would you expect here? How many different paths are there? Looks like 4 or 3. What do you think? I usually start with the battery, for instance. What resistors would be considered on the same path as the battery? One, 2, and 4. The problem is if you imagine traveling out of the positive terminal of the battery, you pass through R1. So the battery and R1 have to have the same resistance. But as soon as you hit this junction, what happens to the current? It's going to split, right? So that current splits into 2 different currents, let's say I2 and I3. But then I2 and I3 join back together. And when they join back together, getting the current through R4, note that that path continues. So R4, the battery, and R1, this is just one path. So it just has one current. So it looks like we really only have 3 currents here. There's the current through this branch with R4, the battery, and R1. That's just one path, so it has one current. There's the current through resistor 2, and there's the current through resistor 3. And the junction rule actually governs how we're going to be combining those. If you take a look at this junction, what equation could we set up using the junction rule? What do we know about how those currents are related to each other? Yeah, we know I1 has to equal I2 plus I3. This goes back to the idea that the total of all of the incoming currents has to equal the total of all of the outgoing currents. At this point, the only current going in is I1. The only currents going out are I2 and I3. So I2 plus I3 together has to match I1. You could also try drawing out a junction rule equation at this point, but you're going to get the same thing. I2 plus I3 equals I1. So that doesn't really get you a separate equation. But we at least know how the currents are related. So if we know any 2 of them, we can immediately find the third one. Any questions on that so far? And then one way to proceed from here is to use the loop rule to get more equations using the same unknowns. If you set up a loop rule with just the leftmost loop, so ignoring this branch, just looking at this loop, you'd have, for instance, 36 volts minus IR minus IR minus IR equals 0. That gets you a second equation with I1 and I2. Or set up a loop rule using the outermost loop, ignoring resistor 2 and just looking at this path. You'd have 36 volts minus this IR minus this IR minus this IR equals 0. That gets you a third equation with I1 and I3. So that would provide a system of equations with 3 unknowns, 3 equations, and you can solve that as a system of equations. But that can be kind of tedious, and it's always possible to set up a system of equations for a circuit like this. But it's often easier to simplify the circuit first. For example, are there any groups of resistors here we can definitely say are in parallel or definitely in series? Yeah, resistor 2 and resistor 3 are connected in, they're in parallel. And that means we can combine them. So we can combine R2 and R3. R2 and R3 are definitely in parallel. We've got 3 ohms and we've got 6 ohms. We want to say that acts like just one big equivalent resistor. The whole point of simplifying a circuit is treating clusters of resistors as acting like just one big resistor and figuring out how much resistance that effectively has. So how would we combine 3 ohms and 6 ohms in parallel? Can we just add those together to get 9? No, what do we have to add instead? Yeah, we got to add the inverses. So we add 1/3 plus 1/6, and that'll give us 1 over the equivalent resistance, which I would usually call R23, because it's a combination of resistor 2 and resistor 3. So 1/3 plus 1/6, and of course we need a common denominator here, so I'm just going to multiply the 1/3 by 2/2, making it 2/6. So we get 2/6 plus 1/6. Combine those, we get 3/6 or 1/2. So does that mean the equivalent resistance is 1/2? What else do we still need to do? Yeah, 1/2 is 1 over the equivalent resistance. So we invert that again and we get 2 ohms. In other words, these two resistors together act like a single resistor whose resistance is 2 ohms. By the way, how does that 2 ohm equivalent resistance compare to these individual resistors? How does 2 compare to 3 or 6? It's smaller, yeah. If you put resistors together in parallel, the resulting equivalent resistance is going to be weaker than any of the individual resistors. Because if you put them together in parallel, if you add more paths, you make it easier for current to flow. If you have a single resistor, resistance makes it difficult for current to flow. If you add another resistor in parallel, it's tempting to think, oh, we've added another resistor, that increases the difficulty. But the important thing here isn't so much that you've added another resistor. The important thing is you've added an alternative path. And if you add another path, it makes it easier for current to flow. Very much like, for instance, if you've got, let's say you have a pipe that water can flow through, and you're having a difficult time with the fluid flowing. If you add another pipe, another path that the fluid can take, you reduce the congestion. You're allowing more freedom of movement, more opportunities to flow from point A to point B. The extra path makes it easier to flow, so it lowers the overall resistance. And if you add another path, and another path, and another path, the more paths you add in parallel, the easier it is to flow. So adding more paths in parallel always reduces the total resistance. Any questions on that so far? So now that we know that those two resistors act like just a single 2 ohm resistor, we can redraw the circuit. And say we've got R1 is 2 ohms and R23 is 2 ohms. We're just combining these two parallel resistors as if they were just one resistor. And then R4 is 5 ohms. But now how are these three resistors connected? And if they're in series, what can we do with those numbers? Exactly. In series, we can just add those numbers directly. 2 ohms plus 2 ohms plus 5 ohms is 9 ohms. So all three resistors, all of the resistors together act like just one big 9 ohm resistor. And notice that 9 ohms is bigger than either of those individually. If you've got resistors in series, the total equivalent resistance is larger than any of the individual resistors, because more resistors in series increases the difficulty. You're keeping just one path, but you're making that path more difficult. But all of these together act like just one big 9 ohm resistor. Our equivalent of the whole circuit is 9 ohms. And this battery is still 36 volts. And the whole point of all this is that we can now say this complicated looking circuit acts like this much simpler circuit. And I find it useful to imagine this as like, imagine all these resistors are in a box. You've built this box that contains some cluster of resistors. From outside the box, all you see is there's a battery with wires that go into a box. And you don't know what's going on inside the box. But as far as you can tell from outside the box, the whole box acts like a 9 ohm resistor. How many batteries are there? Just one, a single 36 volt battery. And sometimes a battery is drawn as just a single short bar and a single long bar, or sometimes it's drawn as several in parallel, several next to each other, I mean, not in parallel. So historically, this would have meant 2 batteries attached to each other in series, but this still just acts like a battery. If you've got several batteries attached to each other in series, they act like just one big battery. So this just means one big battery. Any other questions on that so far? So now that we have a simplified circuit, we've treated this as just one battery and one big resistor. At this point, we just have one path. So there's just one current circulating in the whole thing. And how could we calculate how much current that is? Yeah, at this point, it's just going to be epsilon divided by R. Because our loop rule, earlier, if we had tried drawing out loop rules, it would have been fairly complicated. We get a system of 3 equations, 3 unknowns. But in this simplified loop, our loop rule, delta V battery plus delta V resistor equals 0. We would just get epsilon plus negative IR equals 0. Add IR to both sides, divide by R, and we get I equals epsilon over R. Note that this is only true if the entire circuit consists of just one battery and one resistor in a loop. But the whole point of simplifying the circuit is to reduce it to that if possible. So now we can just divide 36 volts divided by 9 ohms, and we get 4 amps, 36 over 9. So in this simplified circuit that the original circuit acts like, we would expect 4 amps of current. But that should be equivalent to which one of these currents in the original circuit? Which current in the original circuit is going to be that value? Should be I1, yeah. And the reason for that really has to do with what wasn't changed. We simplified quite a lot of this circuit. We combined all these resistors together. What's the one part of the circuit we didn't simplify? What's the one piece of the circuit we didn't combine with other pieces with these simplification formulas? Like we combined resistor 2 and resistor 3, then we combine that with R1 and R4, but we didn't combine that with what else? What's the one value in this that we took directly from the original? Yeah, the battery itself. The battery is the one piece we didn't simplify. So that means that this 4 amps, I mean, we can't really say 4 amps through the resistor because there's lots of resistors. We mushed all those together. But if we conclude that there's 4 amps of current through the battery, this is the exact same battery. Nothing has changed about the battery. So the battery is really the thing we should assume stays the same. We know there's 4 amps of current through the battery. And it so happens that resistors 1 and 4 are in series with the battery, so they have to have the same current that the battery does. When the current hits the junction, it's going to split up. So I2 and I3 have to add up to 4 amps. We can now conclude that anyway. To figure out how much we get, how it splits up into I2 and I3, one way of doing this is by analyzing the voltage on everything else. If we take a look at the voltage of resistor 1 and the voltage of resistor 4, let's see if we can figure out how much voltage is associated with each one of those. How do you calculate voltage of a resistor? Now that we know all the currents. Yeah, delta V is just negative IR. So every resistor, if you know the current and you know the resistance, then you can just multiply those to find delta voltage. For example, R1, 4 amps is the current, 2 ohms is the resistance. Multiply those together, you get negative 8 volts. So that means this resistor 1, involves a voltage drop of negative 8 volts. Likewise, resistor 4, we multiply resistance times current, 4 amps times 5 ohms, and we get 20 volts. So that means resistor 4 is associated with a voltage difference of 20 volts. So across this resistor, from start to finish, we are losing 20 volts. And at this point, I find it useful to start actually labeling voltages. And let's say we put a location right before the battery and we call that 0 volts. So this point is voltage 0 volts. We go through the battery. What does a battery do to voltage? Right, it adds to the voltage. It provides this voltage boost, and we know how much. If we call this location 0 volts, just as an arbitrary reference point, the battery adds 36, so this point would be at a voltage of 36 volts. And by the way, this doesn't have to be 0. We could call this 100 volts, and then this would be 136 volts. The important thing is the difference, but it's usually easier to just call the starting point 0 volts. Then this resistor causes a drop of minus 8 volts because it's got 2 ohms of resistance times 4 amps of current. That means negative 8 volts of voltage drop. 36 minus 8 is going to be 28. So this location has 28 volts as its voltage. Then we go through these resistors. We know their resistances, but we don't know their currents. So we can't really do anything with that yet. We lose some voltage, but we don't know what the voltage is there. But let's backtrack from the other direction. We know this is 0 volts going through just wire. It's still 0 volts. And now we backtrack. We know we start at something, we lose 20 volts, we get down to 0. Backtracking, what does this voltage have to be to make that work? Yeah, this is going to have to be 20 volts. Because you've got to be able to lose 20 volts and end up at exactly 0, because you get back to the starting point. This is effectively just a graphical way of doing the loop rule. These voltages add up to, or voltage differences add up to 0. Plus 36 minus 8 minus something minus 20 equals 0. And now that we know the voltage here and the voltage here, we have the delta V for both of these resistors. Each one of these is involving a drop of 8 volts. So we can now confidently say that resistor 2 has a delta V of 8 volts. In fact, if we're just trying to solve for I, we can isolate I preemptively. I equals negative delta V over R. We know for resistor 2, the delta V is 8 volts because we're going from 28 to 20. For resistor 3, the delta V is also 8 volts because we're going from 28 to 20. They're in parallel, so they both get the same full voltage drop. In this context, the full voltage drop is minus 8 volts. So I2, we've got negative 8 volts from 28 to 20, divided by this resistance, 3 ohms. So we get 8/3 amps, or 2 2/3. For current 3, we got negative 8 volts. It's getting the same full 8 volts because it's the same starting point, same ending point, divided by 6 ohms. 8/6 reduces to 4/3, or 1 1/3 amps. So we now know both of these currents, 2 2/3 amps, 1 1/3 amps. As a couple of final checks there, what do those add up to? 2 2/3 plus 1 1/3? Yeah, those add up to the 4 amps that they should due to the junction rule. You got 4 amps coming in, it splits up 2 2/3 amps, 1 1/3 amps, and then those join back together, adding up to 4 amps again. So this all checks out with the junction rule properly, as it should. And also, how do these compare to each other? What's the ratio there? Yeah, 2 2/3 is twice as much as 1 1/3. Note how that compares to the resistance. Resistor 2 is half as much resistance as resistor 3. 3 ohms is half as much as 6 ohms. Half as much resistance means twice as much current, because current and resistance are inversely proportional if voltage is constant. So this all checks out. The one with half as much resistance gets twice as much current. The least resistance gets the most current and is proportional. And they add up to the incoming current that they started with. So these parallel resistors split up the available current proportionally, and they share the same full voltage. They both get the same full voltage. Any questions on that? So that's the basic idea of circuit analysis. Simplify the circuit as much as you can. Use that simplified circuit to find the current through the battery. Once you know that, go back to the original circuit, fill in all the currents you can, start filling in voltages, and then see how the current splits up on parallel branches like that. So get some practice with that. If you go to math.ancheese.org/P7B, there should be a circuit analysis worksheet there. It doesn't really have any instructions. It's just a bunch of circuit diagrams. But the idea is on each one of those, the resistances and batteries are labeled. Your task then would be to find all the currents, basically doing the same sort of analysis we did here. So give that a try, get some practice. Feel free to bring that into office hours if you want some help, and I will see you next time.